Hi everybody. So we're skipping a chapter. I'm not going to do chapter 7. Seems to be a popular decision to skip chapter 7 and go directly to chapter 8. Chapter 8 is kind of fun. I can understand why people do that. It's about ODEs, ordinary differential equations. The ordinary means as opposed to partial differential equations. So in this case, the functions we're trying to solve for is a function of just a single variable. Actually, we'll also be able to handle systems of ordinary differential equations. So we'll have systems of equations in several functions, but each one will only be a function of a single variable. Now, I'm sure you've seen a little bit of this before in calculus. So let me just review a simple example of a differential equation. Take the equation y prime equals r times y, where r is a constant, right? So r is some constant. Y is the dependent variable of the function of x, and we want the derivative of y to be proportional to the value of y itself. If I rewrite this slightly, I'm going to rewrite y prime as dy dx, and I'm going to bring the y from the right side over to the left side, write it as 1 over y, and I'll leave the r on the right side. Okay? The reason for doing that is that now I can integrate both sides with respect to x. So I can integrate with respect to x on the left side and integrate with respect to x on the right side. And what happens is that because of the substitution rule in integration, I can replace dy dx dx by simply dy, and that means the integral on the left side only involves y now, whereas the integral on the right side does not involve any y's, so we can just integrate it directly. Right? So in fact, on both sides, we can just compute the integral because we've separated the variables. We have only y's on the left side and only x's on the right side. So this is called the separation of variables technique. It's a simple way to solve simple differential equations. So on the left side, we get log y. On the right side, we get rx. I'm throwing in a constant of integration. We only need to throw in one constant of integration per equation, even though there were two integrals, right? So we can kind of absorb both constants of integration into one, right, for a single equation. Solving for y, we exponentiate on both sides, so y equals e to the c times e to the rx. E to the c is just another constant, right? I mean, c was a constant, so e to the c is just another constant, so we can rewrite it this way, and we get a familiar-looking equation. This is the equation for exponential growth and decay, and it's used for population growth, it's used for radioactive decay. The constant c prime here represents the initial size of the population, or the initial size of the mass of the radioactive material that's going to be decaying. R represents the decay rate, or population growth rate. And so this is used for, let's see, for continuous interest in finance, and as I said, radioactive decay, population growth. What all those situations have in common is that the rate at which the quantity y is growing is proportional to the current size of y. So they all satisfy the same differential equation. And therefore the solution has the same form in all those cases. Okay, the general form of the ODEs we'll be solving is y prime equals some function of x and y. So note that in this case, f of x is not y, it's y prime, right? And it's a function of two variables, whereas y is only a function of one variable. Let's see. So the actual function we're solving for, y, is only a function of one variable. Now, if we assume that the initial value of y is specified, right? So we're trying to solve this differential equation, usually on some finite domain, especially for numerical purposes. We're virtually always trying to solve it on a finite domain. We're not trying to get a general solution. So x0 is the left endpoint of the interval we're trying to solve this function on. And if we're given the corresponding y value at the beginning, if that's specified, then this is called an initial value problem, right? Because we've got the initial value of the function y, and we're trying to fill in the successive values. And in general, this will have a unique solution. So there's a quite general result in differential equations that says an initial value problem will have a unique solution. Not surprising if you know the starting value, right? If you know the starting value, you're given y of x0, and if you know the rate at which y is changing at every moment, then it's not really surprising that you should be able to track y, at least in principle, you should be able to track y exactly through the whole course of its evolution. However, it's easy to write down equations that look simple, differential equations that look simple, but are difficult to solve. This is one. I kind of made this one up, and I tried it out on Wolfram Alpha. Wolfram Alpha did not know how to solve it, so I assume this is a difficult differential equation to solve formally, to get a complete mathematical solution for. However, we're doing numerical analysis. It won't be that difficult for us. We'll be able to find solutions to this differential equation, or I should say approximate solutions, right? Because we're just getting numerical approximations to the true solution. So before I get into the details of solving ODEs numerically, I'd like to show you kind of a nice way of representing ODEs visually that gives you a lot of insight into what the solution would be. Recall that these ODEs that we're looking at are of this form. So we've got a function f that tells us what y prime should be at every point in the xy plane. Right? Y prime, of course, is the slope of the curve we're looking for, right, of the function we're looking for. And so if we know the slope at every point, every potential point where the curve might wander to, then what we do is we represent all those slopes. And a convenient way to represent slopes is with vectors. So what we do is we plot vectors that point in the same direction as y prime at a representative sampling of points in the xy plane. So that's what a vector field is. Vector field is basically a function that defines a vector at every point in the field. And when we represent it visually, we take a subset of those points, a representative sampling of points, and graph the vectors at those points, and that's, hopefully that's enough to give us a good feeling of what the vector field in total would be like. So how do you represent a slope y prime with a vector? Well, if the slope is y prime, then we represent it by the vector where the x component is 1 and the y component is y prime itself. And that way the slope of the vector will be exactly y prime. So, simple thing to do. Take a bunch of points in the xy plane and plot the corresponding vectors in those points, and then we can actually see what the function f looks like. Okay, so I'm going to do this with the example y prime equals cosine x plus sine y. Right? Difficult to solve formally, but you can see that by plotting a vector field in MATLAB, we'll actually get a very clear idea of what the solution would be like. Now before I switch over to MATLAB, let me just go over some of the commands I'm going to use. There's the mesh grid command, and in mesh grid takes two arguments. You give it a list of x values and then a list of y values. And it returns two arrays, and I'm going to write them to the variables x and y. The first array is just the array of x values, and the second array is just the array of y values. So because this list of x and y values kind of represents a rectangle in the xy plane. By the way, the x values go from 0 to 5, and that means that there's going to be 6 x values. The y values go from 0 to 4, so it means there's going to be 5 y values. And each of these matrices, therefore, will be actually 5 by 6, because awkwardly with matrices, we always give the number of rows before the number of columns, even though the number of rows, in a sense, corresponds to the vertical dimension, and the number of columns corresponds to the horizontal dimension. So it's a little bit awkward since it's kind of the reverse of what you expect from working with Cartesian coordinates, right? The Cartesian coordinates, you give the horizontal component first and the vertical coordinate second. Anyway, we'll live. Let's see. So this is going to return two 5x6 arrays, and going to represent the x and y coordinates respectively at all the points in this rectangle in the xy plane. So our rectangle is going to go from x equals 0 to x equals 5, and from y equals 0 to y equals 4. And it's going to be broken up into, well, it's going to be segmented into units, right, into whole values of the coordinates. The first row of the x vector will be the numbers 0, 1, 2, 3, 4, 5, right? Because the first row of the x matrix will represent the coordinates along the x-axis itself when y equals 0, right? Now, all the successive rows of the x matrix will be exactly the same. They'll all be 0, 1, 2, 3, 4, 5. Whereas the y matrix is going to represent the y coordinates, so that'll work a little differently. The first row in y will be all zeros, because those points on the horizontal line where y equals 0, they all have the same y coordinate 0. Whereas the second row in y will be all 1s, and the third row in y will be all 2s, etc. Okay, so x and y will represent the x and y components of the coordinates at the rectangle that we described here, right, from 0 to 5 along x and 0 to 4 along y. Then I'm going to define the function f. By the way, you're going to want to make sure that the function f can handle vector inputs. I didn't have to do anything special here because cosine and sine already will handle vector inputs. But sometimes, oh, and I should say that also the plus sign automatically will handle adding matrices or vectors of the same dimension. But in other cases, with a more complicated looking function, you might have to put some dots in there, like dot times or dot power or something, to make sure that it's able to work with vectors. Now, dx is going to represent the matrix of the x components of all the vectors in the vector field. That's easy because, as I said here, when we represent the slope, we represent it by a vector whose x component is always 1. So that's not going to be a problem. We just let dx be a matrix of 1s. So remember, this is a 5x6 matrix, just like x and y are, right? 5 rows, 6 columns, and it's all 1s. Okay. The matrix dy is going to represent the y components of all the vectors, of all the arrows, and that's just given by plugging x and y into f. And this is why f has to be able to handle, in this case, matrix inputs. Right? Having that done, then we call the MATLAB command quiver, which takes 4 inputs and an optional 5th input. The first 2 inputs are just the x and y coordinates. The second 2 inputs are the x and y components of the vector field, and the 5th optional input is a scale factor. You can make the arrows bigger or smaller to please your eye, right? Sometimes if the arrows are too big, they seem too crowded, and if they're too small, they're hard to make out, so you can scale things up or down with that last entry. Okay, let me switch to MATLAB now. So, first of all, I'll define the x and y vectors, or matrices rather. So we use the mesh grid command, and we want x to go from 0 to 5, we want y to go from 0 to 4. So this will define a 5x4 rectangle on the xy plane. And here you can see, so x, each row of x is 0, 1, 2, 3, 4, 5, and the rows of y are constant, but they increase as you go down. All right, so they're just giving you the x components at each cell of the rectangle, right? So it's like we've taken this 6 by 5 rectangle, and we've broken it up into 30 individual cells, and these numbers are the x and y components respectively at each cell. Okay, now we have to define the function f, so that's going to be, it's a function of two variables. You can just use the at symbol again. No matter how many variables your function has, you can do it basically the same way. And this is going to be cosine x plus sine y. Okay, now we have to define the dx vector. Now remember, this is the, I'm sorry, not vector, matrix. This is the matrix of the x components of all the vectors in the vector field, and they're all ones. So ones, and we want this to be a 5 by 6 array of ones, right? Because the vertical component are the y values going from 0 to 4, and the horizontal component are the x values going from 0 to 5. Okay, so those are all ones. And then dy are the y components of the vectors, and that we just get from applying the f function to the x and y values. And so it'll be able, it'll take each x value and each y value from corresponding locations in the respective matrices and apply f to them, and then fill up the matrix. So there we go, there's f. And now we can call the quiver command, and I'll give it x, y, dx, dy. Let's see what that looks like, and then we'll just see if we want to scale it up. Let me see. Here's the figure. There we go. That's not bad. So you could, maybe it could have been a little denser to get a finer grained, a more fine-grained analysis of what the vector field looks like. But you can see that, you know, suppose you started here, then you can kind of visually trace out what the solution would look like. It would be a curve that kind of goes like that. And notice if you start at different starting points, you know, you're free to start at any given y value you want, then you're going to get different curves, right? And in some cases they might be radically different by changing the initial y value. By the way, let me see, if I wanted to scale it up, I could throw in, for example, I don't know, how about 0.8? I'll scale the arrows down just a little bit, make them smaller. Maybe that's a little bit easier on the eyes. I don't know. But okay, so by doing this, you can get a pretty good idea of what a solution ought to look like. Maybe, let me try this. I'll redo my x's so that I'll do them, instead of doing them by units, I'll do them by intervals of half units. So how about 0.5 and 0.5? I think I'll suppress the output here. Okay, but now there's going to be 11. Let me get this straight. From 0 to 5 going by halves, it's going to be, we're going to have 11 x values, and we're going to have 9 y values. Okay, so I have to redo dx. dx is going to be now 9 y values and 11 x values. Right? And dy I can just recalculate. Okay, and then I'll do quiver again. Let me leave the scale out. What does that look like? Oh, that's pretty good. So that gives you an even clearer idea of, you know, how the vector field works. So it's going to, if you started at 0 on the left and trace the path that you're carried along, you see you're going to get some kind of curve like that. And so you can visually see what the solutions are going to look like. Okay, now there's one other topic that the author mentions in the textbook that I should go over, stability. And it basically corresponds to the butterfly effect, right? What happens if you make a small change in the y value at the beginning? How big an effect can that have on the solution overall at later points in its evolution? So one way to analyze this is to say, look, let's suppose that capital Y here is the true solution to a given initial value problem when y of x0 equals some specific value y0. And then we'll let y sub epsilon denote the true solution to the slightly different initial value problem when y of x0 is y0 plus epsilon, right? So we just tweaked the initial value of the function a little bit, and we want to know what possible effect could that have on the evolution of the function for other x values that come later. Right? By the way, I often think of x value as being time in this case, so you can think of the function y developing over time. Not always the case in applications, but it seems like a convenient way to think about it. Okay, so we say that an ODE is stable on a particular interval from x0 to b, right? We're always working on a particular interval that we're trying to find a solution on. So we'll say that an ODE, a differential equation itself, not the solution, but the differential equation itself, is stable if there is some constant c, some positive constant c, for which the maximum difference between y epsilon and y at any point x on the interval we're interested in is less than or equal to c epsilon. So the maximum difference is bounded by a constant times epsilon, right? Where epsilon is the initial difference. So this is saying that things do not spiral out of control. If you start with a small difference epsilon in the initial value, then at any later point x in the evolution of the function, the difference in the y values will still be basically just some constant times epsilon, right? And, oh, by the way, and this, I should say that this is under the assumption that epsilon is sufficiently small. We don't require this for every conceivable epsilon. We don't require it when epsilon is equal to 1,000,000, for example. But we just say that this should be true for sufficiently small epsilon, right? So at least in some neighborhood of 0, this should be true. Okay, let's see. Now, even if an ODE is stable, it could still be poorly behaved if the value c is large, right? If this constant c is very large, then that still leaves open the possibility that there could be big differences in y values, right? Resulting from even just a small difference in the initial y value at x0, right? Epsilon is the initial change in the y value. Even if that's small, if c is very large, then we could get very large differences in y down the road, okay? So in that case, we say that it's ill-conditioned. It's formally stable, but it's ill-conditioned. There's a lot of terms like this, ill-conditioning and stability. Remember, ill-conditioning, or the condition number came up with matrices. It becomes a big issue in numerical analysis. Some problems, although in principle they have nice solutions, in practice, making small errors at some point can really balloon into big errors down the road, and we have to pay attention to all that. Now let me just make one other note about notation. Of course, we're working on ODEs here, so the function we're trying to solve for is a function of only one variable. However, this function f that actually tells us what y prime is in the differential equation itself, f is a function of two variables, potentially. And therefore, we're actually going to have to take partial derivatives of f, even though the differential equation itself is only an ordinary differential equation, meaning that we're only taking the ordinary derivative of y is a function of one variable. So I just want to get the notation straight because it can get a little confusing. I'm going to denote by f sub x the partial derivative of the f function with respect to its first argument. Okay? And I'm going to denote by f sub y the partial derivative of the f function with respect to its second argument. These are both distinct from the total derivative of f with respect to x, That is, if you imagine that y actually represents a true solution to the differential equation, so you think that y itself is a function of x, then you can take the ordinary derivative, the total derivative of f with respect to x, and in that case, so think of it this way, where we're thinking of the y argument as being the true function, the true solution to the differential equation, so it's a function of y is a function of x. And the way you take the total derivative is you first take the derivative with respect to the first argument, and then you take the derivative with respect to the second argument and multiply by y prime. So you probably did this kind of thing if you took M310. You talk about partial derivatives and total derivatives. So we're just tracing the dependence of f through both its first argument in x and its second argument in y. They both depend on x, and we have to get the total derivative, we have to take both into account. Okay. Now, one other thing to mention: what can make the numerical analysis of these differential equations difficult? One thing that can make it difficult is if the derivative with respect to the second argument of f, that is f sub y, if f sub y is positive, that can cause trouble, because think about what that means. If f sub y is positive, that means as you increase y, you also increase y prime, right? This means that as y gets bigger, f is actually getting bigger, and f, of course, is equal to y prime. So as y gets bigger, y prime gets bigger. What consequence would that have? Well, suppose you add a little error term to the y value here, right? Suppose you introduce a little error into the value of y, and then you try to compute y prime using the erroneous value of y. Well, because fy is positive, this value of f is going to be bigger than the value you would have gotten if you'd used the correct value of y. And so this f will be bigger, right, than the value with the correct value of y, and that means you're now going to be using a bigger y prime than you would have been using otherwise, right? So y prime is bigger than it would have been, and therefore y is increasing faster than it should. So if you're using a formula like this to estimate the value of the derivative, which we're going to do in numerical analysis, introducing an erroneous value for y gives us an erroneous value for y prime that's too large, and therefore y prime, which was already too large, is going to start increasing even faster than it should, which means the y value is going to become even more inaccurate at a faster rate. So you can see that's what I mean by you get a kind of a positive feedback loop, that the bigger the error that exists, the faster that error is going to grow in the future. And same thing holds if epsilon had been negative. Same kind of thing happens if epsilon is negative. If the y value is too small, then this is going to cause y prime to be too small, and y will increase too slowly. So again, you're going to get an even bigger inaccuracy in the future as a result of a small initial inaccuracy. So for that reason, we say that an ODE is well conditioned if this derivative, f sub y, is always less than or equal to 0. Right? Never becomes positive on the interval we're working on. Okay, so that would be a well-conditioned ODE. Okay, so with all that preparation, we'll be able to go on to one of the simple methods for numerically solving ODEs in the next video, the Euler method.